This is lecture 30. So in this lecture, we're going to discuss about the parallel resonance. In the previous lecture, we discussed about the series resonance. Right there, we have seen only the voltages, that is series. So in series, the current will be same, and the voltage will be divided. Now in this here is opposite, right? Now in this is a parallel, so current will be divided and the voltage will be same. So whatever the equations we got in the series resonance, so it will become for the current levels, right? So there we have got only for voltage. Now so we can go very quick because it's a same as the previous resonance, but only the variation is currents here, right? Now it's a time domain, so we to find the resonance conditions under the voltage levels under the what is the minimum impedance or maximum, right, currents, etc. So we need to convert into phasor domain. So this is a phasor domain circuit, that is the small it will become capital I and everything will become capitals, that is small I r t will become capital I, IL, IC and V, and this R is R only in phasor domain, but L will become j omega L and omega C will become 1 by j omega C. Now how to find the resonance condition? Now again two ways. So either we apply the KCL or Nodal Analysis or simply find the impedance here. Now if I find impedance, if you see these three are in parallel, so it will become very complex to find the impedance. Now what we find here is the admittance we will find. So admittance if I find, it will be simply added here. So that is y is equal to, what is the admittance here? It is 1 by r plus, again what is the admittance here? 1 by j omega L plus, what is the admittance? 1 by j omega C. So it will become 1 by r plus 1 by j omega L plus j omega C, right? Now if I take j common, so it will become 1 by r plus j, so omega C is the positive, minus C, j is coming up, so it will become minus 1 by omega L, right? So this is the y. Now what is the resonance condition? At resonance, the imaginary part should become 0, right? So that is imaginary part should be 0. So what is the imaginary part? Omega C minus 1 by omega L equal to 0, right? So what is this? Omega C is equal to 1 by omega L. So we can write simply omega is equal to 1 by, omega square is equal to 1 by LC. Here omega equal to 1 by root LC, right? So this is the resonant frequency. So this can be written either omega naught or omega R, right? So what is the resonance frequency in this parallel RLC? Also we are getting same, that is 1 by root LC, right? So at omega naught, so the imaginary part will become, right? So that is omega naught is 1 by root LC, or omega R is equal to 1 by root LC. Now at resonance, now see the circuit will become purely admittance, right? 1 by R means R conductance. So that means at resonance, y is equal to simply 1 by R, right? Now in the previous case we said Z is a minimum at resonance. Similarly here y is minimum at resonance, right? So if y is minimum, what happens to Z? So Z is equal to 1 by y. So 1 by minimum is equal to, we'll get what? 1 by R means R only, but this is the maximum we will get. Z will be maximum in parallel RLC circuit. So again I am repeating. So at resonance y is equal to 1 by R. So is it at a minimum level? But we need Z impedance. So impedance will become the maximum at resonance. So opposite of the series resonance circuit, right? So this is using the impedance or admittance. So we can find from the current expressions also. So what is the current expression? The total current I is equal to the resistance current plus inductance current plus IC, right? So this can be written like this. So IR is equal to V by R, IL is equal to V by j omega L plus V by 1 by j omega C. So if I take V common, again it will become 1 by R plus J omega C minus 1 by omega L. So this is I, right? So this can be written like this. So at resonance, omega C minus omega L will become 0, right? Omega C minus 1 by omega L equal to 0. Or, so what is this? V into J omega C is nothing but IL should be equal to IC. So we'll take mod. So this is the resonance condition. That is, so this is already we got. So what is the resonance condition? At resonance, the magnitude of inductor current should be equal to the magnitude of capacitor current, right? So at resonance, right? Now we will write what is this IL and IC as we written for VL and VC. So what is IL? V by J omega L, right? Now what is V? See here. Now at resonance, this imaginary part is becoming 0. So I will write first what is I? I is equal to V by R, right? So this is the important condition, right? And see here, the source current and the resistance current or the voltage is in phase. So I is equal to simply IR, because IR is equal to V by R, right? See here. So what is V? V is equal to I into R by J omega L. Now how can I write this one? So I into, so previously we have written V into Q. So R by omega L as I am writing as Q, and J is becoming minus 90 degree. Now what is Q here? R by omega L. It's the opposite of the series resonance circuit. See here, IL is equal to in terms of current and in terms of Q factor, or simply again write I into R by omega L. So it is angle minus 90 degree, right? Now again, the inductor current is greater than the source voltage, source current, right? Yes or no? So I into some magnitude is there, so always it will be greater than the source current. Similarly, IC is equal to V by 1 by J omega C. So it will become I into R into omega C angle 90 degree. So if I replace R omega C, omega RC is by Q, so it will become I into Q angle 90 degree. So these are the very important parameters, IL and IC. So I into Q, right, angle minus 90 degree, right? So one more expression we need to write, that is XC. XC is here what? Omega C 1 by omega C J omega C. So it will become what? So 1 by C angle minus 90, etc. So depending on that also we can write. So it's anyway, it's not required, right? Just remember I into Q and what is Q factor, right? Now we will draw the frequency response curve, right? Now, so what is the Y? Y is equal to 1 by R plus J into omega C minus 1 by omega L, right? And what is I here? I is equal to V, if I take common, so it will become 1 by R plus J into omega C minus 1 by omega L. Now what is the magnitude we will get? Mod I. So mod V into square root of 1 by R whole square plus omega C minus 1 by omega L whole square. Similarly, what is the mod Y? Mod Y is equal to 1 by R plus, C square root of omega C minus 1 by omega L whole square. Now for Y, I will write here, right? So this is with respect to omega, this is mod Y, right? Now at omega equal to 0, so this is 0 and this will become 1 by, what do you call, 1 by 0, right? 1 by 0 means infinity, minus infinity square, so we'll get like this. So infinity and so on, infinity. But at a resonance, omega naught is equal to 1 by root LC, we'll get Y min. But the same, if I go for the impedance, this is Z, mod Z. So it will be opposite of this one. something like this. See, y equal to infinity means z is equal to 1 by y, so it will become 0. So it will be something like this, right? So at omega naught is equal to 1 by root LC, you will get z max, right? Wherever the admittance is minimum, so we'll get z max. So z max is directly r. Y min is equal to 1 by r, right? So we can write either this one or this one. Now what is the current response, frequency response? This is omega and this is mod. Now very simple. Now wherever the impedance is low, we'll get maximum current. Wherever the impedance is maximum, we'll get minimum current. So this will become opposite of this. See here. Now R, simply if you substitute here omega c equal to omega equal to 0, right? So we'll get 1 by omega 0 means 0, 1 by 0 means infinity, right? So what we will get? Infinity, and it will decrease and it will increase again. So at resonance, omega naught is equal to 1 by root LC. So what we will get? We will get I minimum. Now if I want to find the bandwidth, so we need to find V omega 1 and omega 2. So what is the bandwidth? Bandwidth is equal to omega 2 minus omega 1. Now to find the bandwidth, so we need the values at omega 1 and omega 2. Now if I assume I min is equal to some Im, so at here, see, this is greater than this. So this at omega 1 will get some current as greater than this. So it will be actually at 3 dB means we'll get above 3 dB. That is, it will become root 2 times Im at omega 1 and omega 2. Right? So this is the frequency response of the current. Now if you see at resonance, it is becoming the current is minimum. That means this circuit is called rejector circuit. Rejector circuit. We called the series resonance circuit is called acceptor because at resonance the current is maximum. So this one is generally called rejector. Now we'll find the what we call bandwidth. Now we know that. So what is the current? So I is equal to V by Z, or simply V into Y. So what is V? So V is V into Y means 1 by R plus J omega C minus 1 by omega L. So this is the current I. So 1 by R plus J into omega C minus 1 by omega L. So this is we got in the now only the previous first 5 minutes before, right? Now what is I is equal to V into 1 by R. So what is the magnitude? So magnitude is equal to or Im, maximum or minimum mod I is equal to, this is V, so we can say mod V also, square root of 1 by R whole square plus omega C minus 1 by omega L whole square, right? Now we will find, so this is a minimum, right, at resonance. So it will become Im is equal to, simply I will write Vm or simply V, right? So write Vm square root of 1 by R whole square plus omega C minus 1 by omega L whole square. We know that at omega is equal to omega 1 comma omega 2. So both frequencies, what is Im will become Im by root 2. So this will be equating with the Im by root 2. Then we can get the omega 1 and omega 2. That is like this. So what is Im? So Vm square root of 1 by R whole square plus omega C minus 1 by omega L whole square is equal to simply Im into root 2. But what is Vm? We know that is Im into R, the square root of 1 by R whole square plus omega C minus 1 by omega L whole square. So this derivation you can do also, right? So Im cancel. So this is R is going that side. And if I squaring both sides, if I square both sides, right? So squaring both sides. So what we'll get? So here 1 by r whole square plus omega c minus 1 by omega l whole square is equal to square root means it will be 2, and this is r, so r square, and it will become 2 by r square. So what is this? Omega c minus 1 by omega l whole square will become 2 by r square minus 1 by r square, simply 1 by r square. So what we need? Omega c minus 1 by omega l will become, see it's a square root, right? So we'll get plus or minus 1 by r. Now to find omega 1 and omega 2, we'll take one at a time. So if I take positive omega c minus 1 by omega l, so we'll get 1 by r. Similarly, omega c minus 1 by omega l will become minus 1 by r, right? Now it's a become quadratic expression. So it will become omega square LC minus 1, which will become omega L is going that side, so it will become omega L by R. It's just a mathematics manipulations. So we need omega square, that is in quadratic expression. If LHC is going like this, so this is minus omega L by R. So LL cancels, so it will become minus omega by RC, right? Minus, this is LC is dividing equally, so 1 by LC equal to 0, right? So is this right? So LC means LL cancel RC. Now this is the quadratic expression. What is this? Omega minus B, minus of minus plus. So plus 1 by RC minus B plus or minus root of B square minus 4AC. That is 1 by RC whole square minus 4AC. So minus minus plus 4 by LC by 2. Right. Similarly, I will write for this one also. This will become like this: omega square LC minus 1. So this will become here plus, right? Plus, so omega C by R is equal to 0. So divided with LC, so we'll get omega square plus omega by RC minus 1 by LC equal to 0. So again, what is omega? Minus B, that is minus 1 by RC plus or minus root of B square, that is 1 by RC whole square plus 4 by LC by 2, right? So this is the one. Now from this we have to take only the positive roots. So now if you see this, so this is the only positive, that means it will be maximum frequency. So from this we will get omega 2 is equal to 1 by 2 RC, because 2 is there, plus square root of, inside it will become 1 by 2 RC whole square plus 1 by LC. 4 will be cancelled. Similarly, this is the minimum, so we will get omega 1, which is minus 1 by 2 RC plus, as it is same, into square root of 1 by 2 RC whole square plus 1 by LC. Now we may ask why we have taken only positive terms, right? Now see here, if we take the negative, so we may get the negative frequency, but if you see the frequency response, we have to get the only positive frequencies. So here also, if you take minus minus, it will become negative frequency. So that's why we are taking the here positive and here also positive, right? Now whenever both are positive, so we'll get a maximum frequency, right, compared to this one. So that's why it will become omega 1 and it will become omega 2. Now we got omega 1 and omega 2. So what is the bandwidth? So bandwidth is equal to omega 2 minus omega 1. Now if you see, these two are same. So if I take subtraction, means it will be cancelled. Simply 1 by 2 RC minus of minus 1 by 2 RC, which will become 2 by 2 RC. So what is the bandwidth? 1 by RC. This is the bandwidth in parallel resonance circuit. The series resonance circuit we got R by L. So you can verify the previous lecture. Right, now bandwidth is over. Now what we need to find? The quality factor Q. Quality factor Q. So it's very simple again. So I'm not going to discuss about the Q is equal to 2 pi into energy stored, maximum energy stored in the circuit by the total power dissipation or power dissipation per cycle. So it will become Q is equal to simply omega naught RC. So just follow that equation, you can get omega naught RC, or it will become 1 by omega naught L by R, So it will become what? R by omega naught L. So this is the quality factor in parallel RLC circuit. Now how can we get this one? We know that R, I can write like this: Q is equal to, if I take the inductor voltage by the current, or it can be written IC by IL, not IC by I, not IL. Now if I take IL by I, so what we'll get? C. IL means what? So this V by J omega L, by I means I is equal to simply V by R. Yes or no? Now, so V will be cancelled, right? So what is this? Will become 1 by J omega L by R. See here. So 1 omega naught L by R. So we have to take the mod. So it will become simply R by omega naught L, or simply omega L also, right? So omega naught by L. Similarly, so that means what? The Q factor is the magnitude of the load current versus magnitude of the source current, or simply magnitude of the collector current and source current, or this can be written on more like this: Q is equal to mod of IL by mod of IR also, because IR is nothing but the source current at a resonance. So these equations are very important, right? Now what is the relation between the Q factor and bandwidth? That also we need to find, right? So we got bandwidth is equal to 1 by RC. What is the Q factor? Simply omega naught RC, right? Now see, 1 by RC is the bandwidth, right? So what is RC? We'll get bandwidth. I mean, from this RC will become 1 by bandwidth. So RC means 1 by bandwidth. So what is the Q factor? Q factor is equal to resonant frequency by the bandwidth. So this we can be written omega naught by omega 2 minus omega 1. Right? So same expression as we got in the series resonance circuit. Right? Now we need to find one more parameter, which is zeta, right? The damping ratio. So for that reason, I will write the nodal analysis, that is I of t or L C. This is V of t. So how can I write nodal analysis? So I of t is incoming. So I of t is equal to all are leaving. So it will become V of t by R plus 1 by L integral V dt plus C into dV by dt. If I differentiate this equation again, so what I will get? C dV square by dt plus 1 by R dV by dt plus V by L is equal to I dash of t, right? Now it will become d square V by dt square plus 1 by RC dV by dt plus V by LC equal to I dash of t by L, right? Now to find the complementary function, so what is this equation will become? So if I convert into Laplace domain, Laplace transformation or Laplace domain, so it will become S square V plus 1 by RC into S into V plus 1 by LC into V is equal to 0 to find the complementary function. Now so this will become what? So this will become S square plus 1 by RC into S plus 1 by LC is equal to 0, right? Now because V cannot be 0. Now so I told you to S square plus 2 zeta omega n S plus omega n square. So compare these two equations from the control system just now. Just for this, just remember this equation. So when we discuss in control system, so what is this quadratic expression, right? From the time domain responses we will see there. So if I compare this one, what is omega n? It's natural frequency 1 by root LC. What is 2 zeta omega n S, or 2 zeta omega n is equal to 2 zeta omega n is equal to 1 by RC. So what is 2 zeta omega n is 1 by root LC, so is equal to 1 by RC, right? So what we will get? Zeta is equal to 1 by 2 RC. So So this is 1 by root LC. If this is going that side, so it will become root LC. So CC will cancel, so it will become 1 by 2R root of L by C. And this is the damping factor, damping ratio in the parallel RL circuit. Again, we need to find the relation between the Q factor and the zeta. So same, what we got, Q factor is equal to omega naught RC. Right? Again, what is omega naught? We know 1 by root LC into RC. So what is this? So what we'll get? This is R into CC cancel, so it will become root of C by L. This is the Q factor, right? Now if you compare these two, so here 2 is missing and this is R and this is root of C by L. That is opposite of this one. So I can write simply, it will become 1 by 2 zeta. Now what is zeta value? So if I write 1 by 2 into 1 by 2R into root of L by C. So 2 cancel. So 1 by R means it will be going up. So R into root of, so 1 by root of L by C, it will become root of C by L. That means what is the relationship between Q and this damping ratio? Q is equal to simply 1 by 2 zeta. Right? So this is about the parallel resonance. Now I will write the summary of this parallel resonance circuit. So we'll write summary here of parallel resonance. Right? So what is this? So what we need to find? First one. So Y is equal to 1 by R at resonance. So that is, it's a purely the admittance, or we can say Z is equal to R and it will become Z max. So at a resonance, so the parallel RL circuit will become purely resistive. Here purely conductive or admittant. Right? So that is the first point. The second point is, or what is omega naught? The resonant frequency 1 by root LC. Now the third point is, what is the bandwidth? Bandwidth is equal to omega 2 minus omega n is equal to 1 by RC. The fourth point is the relationship between the current expressions. This is very important. IL is equal to I into Q angle minus 90 degree and IC is equal to I into Q angle 90 degree. This is the source current, or this can be written I is equal to I into R by omega L angle minus 90. This can also written I into omega RC into angle 90 degree. Right? The fifth one is the Q factor. So Q factor is simply either omega naught RC or R by omega naught L. Now what is the relationship between Q1 bandwidth? Q is equal to the omega naught by bandwidth, resonant frequency by bandwidth. Then what is the zeta value? Zeta is 1 by 2R root of C by L. Right? Now what is the relationship between this Q and zeta? So it will become 1 by 2 zeta. Now we can represent Q in terms of this Q is equal to omega naught RC. So what is omega naught? 1 by root LC. So this will become R into root of C by L. Right? So that means the zeta should become L by C. So just make sure that this is root of L by C, because we got here the zeta is 1 by 2R. So this is the zeta, so 1 by 2R root of L by C. So if you have confusion, just go with the procedure. So we know that Q is equal to omega naught RC and R into C. So omega naught is equal to 1 by root LC. So CC cancel, but root C will be there. So Q is equal to R into root of C by L, and here the zeta is 1 by 2R root of L by C. So don't confuse, right? We will compare the series resonance and parallel resonance, right? So if you remember this this comparison you can easily solve all the problems from the resonance concept. Now we know at resonance Z is equal to purely resistance at Z is equal to R. That means here at V mod VL will become mod VC, right? So that will become omega naught is equal to 1 by root LC, or simply omega also we can write. Now in this case, so this will become purely admitted, that is y is equal to 1 by R, or Z max will become R, right? So here mod of IL will become mod of IC at resonance. So what is the resonant frequency? We'll get same, but in this case the series means voltage division rule, so VL and VC will be equal. Here current division rule, so current will be equal. Next, how to write the voltage expression, that is VL and VC in series. So it will become V into Q, the source voltage into Q factor angle 90 degree. So VL, right? And or we can say Q equal to omega L by R. So V into omega L by R angle 90 degree, because in series, so Z is equal to J omega L. Now same in case of parallel, IL will become IQ into minus angle 90, because 1 by J omega L, or we can say I into R by omega L angle minus 90, right? So just opposite will get, right? But in this case of V will get I, in Q means Q, but Q factor will be R by omega L. Similarly VC means V into Q angle minus 90, because 1 by J omega C, or omega 1 V into 1 by omega RC angle minus 90, right? So this is the opposite, so IQ into angle 90 or omega RC into angle 90. In both cases, this is not IR, this is VR is equal to V. The source voltage will be the resistance voltage. Here the source current will become resistance current, right? Always in series we'll deal with the voltages, in the parallel always we'll deal with the currents. Now power factor is unity at resonance. Similarly here also power factor is unity at resonance. Now what is the bandwidth here? Omega 2 minus omega 1 is R by L, right? Here we'll get 1 by RC, the opposite, and the capacitor will come, right? Next one, how to represent the voltage, the Q factor. So many ways are there. Q is equal to mod of VL, that is inductor voltage, by mod of V, the source voltage, or mod of VC by mod of V, or either mod of VL or mod of VC by the resistance voltage. And Q will become omega naught L by R, if we just substitute here, and Q is equal to R 1 by omega naught RC. In terms of only resistance and inductance and capacitance, it will become Q is equal to 1 by R root of L by C. If you don't remember, no problem, just remember Q equal to 1 omega naught L by R, just substitute omega naught equal to 1 by root LC. Similarly, if you use R and C, so it will be 1 by omega naught RC. And here zeta is equal to R by 2 root of C by L, and the relationship between Q and zeta is 1 by 2 zeta. So same we will get opposite here. Q is equal to mod of IL by mod of I, or mod of IC by mod of I, or mod of IL or IC by mod of IR, the resistance current, the current through the resistance. Similarly, Q is equal to just opposite, 1 by omega naught L by R, so R by omega naught L, 1 by omega naught RC, so we'll get omega naught RC. Q is also opposite, so 1 by R means 1 upon 1 by R means R, and root of C by L. Zeta is also opposite, so 1 by 2 R root of L by C. The relationship will be same, Q is equal to 1 by 2. So this is the comparison between the series resonance and parallel resonance. Just make a chart of this and paste it in your room, just to see always, so you'll get solved all problems if you know this comparison chart, right? In the next lecture we'll see the problems on this series resonance and parallel resonance. Remember, if you want to find the resonance condition, either if it is a series, just find the impedance and make the imaginary part is equal to 0. In case of parallel resonance, it may not be RLC, it may be different two resistances will be given in inductance and capacitance. Just find the admittance and make the imaginary part is equal to 0. Then you can get the resonance condition easily, right? So that we'll see in the next lecture, how to do this resonance problems.